All right, welcome to lesson 4-1, part B. Today we're talking about summation rules, which, considering that 4-1A was all about approximating area, you're probably going to find today's lesson to be completely unrelated, and you're pretty much right. In lesson 4-2, you're going to see how these two ideas are going to come together and actually have something to do with each other. But for today, we are going to review this thing called summation. This is something that you were introduced to in pre-calculus. So you were introduced to this idea of summation, summation notation, and the summation rules. So in front of you, you can see this is the capital Greek letter sigma, which is sort of their equivalent to our S, and that S does stand for sum. And remember, sum is the answer to addition. So what we're looking at today really does have to do with addition. So this is the summation of a sub I from I equals 1 up to n. That's how you would basically read that. And remember, what this means is, whatever this expression is, a sub I, we're using I as a counter. So we're going to start with a sub 1 because it's telling us that I starts at 1, and then plus a sub 2, so the counter ticks up, and then plus whatever a sub 3 is. And you're going to keep on adding until you finally get to a sub n, whatever that n is. And then once you add all of those up, that's what the summation is equal to. So that's what summation is. Hopefully that's at least somewhat familiar to you. Now, just to make sure we're clear on some of the vocab here, that I that you see, in this case, that's referred to as the index. Now, it doesn't have to be an I, although I is generally the most often used, but generally you would see it as I, sometimes J, and sometimes K. Those are probably the three most commonly used letters. Now, it's not that other letters can't be used, but again, if we're talking about what's standard, you're most likely going to come across I, J, or K. All right. The 1 that I equals is referred to as the lower bound. And it doesn't have to be a 1. The lower bound could be any number, but the lower bound is most often going to be a 0 or a 1. And in most of the situation that we're working with in this course, it's going to be a 1. The n up at the top, that's referred to as the upper bound. And then the a sub I, that expression, is the ith term. So in other words, if I is 1, this is the first term. If I is 2, this is the second term, etc. Okay, so hopefully that's a refresher for you regarding summation notation. Now, for summation, we do have a couple of general rules, and given what you've already learned in this course with limits and with derivatives, I think these two general rules are going to seem pretty intuitive to you. Okay, the first of these two rules, and by the way, these rules do need to be memorized, but as I said, once you see what they are, I don't think you're going to have any trouble memorizing them, especially considering what you've already learned in this course up to this point. So the first rule says, if you have the summation from I equals 1 up to n of c times a sub I, where c is a constant, then we can factor that constant out in front of the summation, and you just have the constant times the summation itself. So again, this is very much like what you saw with limit of a constant times a function, or the derivative of a constant times a function. And in both of those cases, you were able to factor the constant out in front, so we can do the same thing here. Now, just to keep in mind the reason that this works, if I were to expand the original summation expression here, that would then equal c times a sub 1 plus c times a sub 2 plus c times a sub 3 plus dot dot dot, finally all the way up to plus c times a sub n. And you'll notice every single term contains a c. And so that means we'd be able to factor out the c, and that's going to leave us with c times the quantity a sub 1 plus a sub 2 plus a sub 3 plus dot 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 plus a sub n. And that expression inside the parentheses is just what the summation of a sub I is equal to. All right, so that's why that particular rule works. Okay, and the second rule, again, something that's going to look extremely familiar to you. If we have the summation from I equals 1 up to n of the sum or difference of two terms, so a sub I plus b sub I or a sub I minus b sub I, then, just like what you did with limits, just like what you did with derivatives, we can then separate this into the sum or difference of the individual summations. So again, these two rules do need to be memorized. I have a feeling you probably have already memorized those. So these hopefully look extremely familiar to you. Okay, so keep these summation rules in the back of your mind. We will be using these throughout the lesson today. Now, in addition to these rules, we also have some formulas, some summations that are always true. Now, these formulas you do not need to memorize, but you do need to understand how and when to use them. Okay, so as I said, these summation formulas, you do not need to memorize them, but you do need to know when to use them so that you can actually look them up. All right, so for the first one, we have the summation from I equals 1 up to n of the constant c. And that's going to just equal c times your upper bound n. Again, this is where c is a constant. And again, if you just think about why this one works, again, if I equals 1, so my a sub 1 is going to be a c, plus my a sub 2, which is still going to be a c, plus a sub 3, which is c, plus dot dot dot, all the way up until I get to my a sub n, which is still c. So I'm adding c n times, and that's why this summation is just equal to that constant times n. All right. The next formula is the summation from I equals 1 up to n of I. Now remember, what this would be then is, when I is 1, we have 1. When I is 2, this is 2. When I is 3, this would be 3, plus dot dot dot, all the way up until when I equals n, and that means we're adding n. So this summation right here, the summation of I, is really just saying 1 plus 2 plus 3 plus 4 plus 5, all the way up until whatever that top number is. And when you add all those numbers together, it's always going to turn out to be n times n plus 1 divided by 2. Okay, the third formula is the summation from I equals 1 up to n of I squared. So again, this would be when I is 1, we would have 1. When I is 2, I squared would be 4. When I is 3, I squared would be 9. So this summation right here is really adding up square numbers, 1 plus 4 plus 9 plus 16, etc. And when you add all of those together, it's always going to end up equaling this expression here, n times n plus 1 times 2n plus 1, all divided by 6. And finally, the fourth and final formula is the summation from I equals 1 up to n of I cubed. And that's going to give us n squared times the quantity n plus 1 squared, all divided by 4. Okay, so once again, you do not need to memorize any of these formulas, but you do need to understand when and how to use them. So let's talk about doing that. All right, so use rules and properties of summation to evaluate the sum. And so here we're looking at the summation from j equals 1 up to 20 of 4j times the sum j plus 1. Okay, so a couple of things to point out here. First of all, notice we're using j instead of I, and like I said, it's not a big deal. It means the same thing. It's just a different letter. Another major difference, though, is notice up here, instead of just having an n, we actually have a specific number. And that means for this particular summation, n equals 20. So in the back of your mind, what you should be thinking about is when we use those formulas, remember all of the formulas that I just showed you were all in terms of n. And that means if I were to use any of those formulas, everywhere the formula calls for an n, we would be using 20. Okay, the other thing that's majorly different here is, notice the expression that we're taking the summation of, it's not just a single term. It's 4j times j plus 1. And none of the summation rules, remember we only had two rules, and neither of those rules talked about the product of two functions. We had a product of a constant times the term, but that's not the same. So what that means is we need to figure out a way to rewrite this so that we can use the two rules that we've talked about. And so the easiest thing to do here would be to distribute the 4j. So that means the summation will become summation from j equals 1 up to 20 of 4j squared plus 4j. So now we're getting somewhere. Now I don't have a product of two different expressions anymore. I just have the sum of two different terms. And that means I can use the second rule now to break this up into the sum from j equals 1 up to 20 of 4j squared plus the sum from j equals 1 up to 20 of 4j. And then now, because each of these has a constant multiplying with the j or the j squared, I can move those constants out in front. So this is now 4 times the summation from j equals 1 up to 20 of j squared plus 4 times the summation from j equals 1 to 20 of just j. And so now we should recognize that this summation right here and this summation right here are both just referring to the formulas that I had just shown you. So that means for this first one, we're going to have 4 times. Now remember, for j squared, let me just write it over here in terms of I. Remember, if I had the summation of I squared, that was going to be n times n plus 1 times 2n plus 1 all over 6. So this is the expression that I need to multiply the 4 with. But remember, everywhere I see an n, that's going to be 20 in this particular problem. So that means I have 20 times 20 plus 1 times 2 times 20 plus 1 all over 6. And then plus 4 times, now remember for j, the summation of just I was n times n plus 1 over 2. So same idea. For the summation of j, I'm going to just use n times n plus 1 over 2, but I'm replacing the n's with 20 in this particular problem. So that's going to be a 20 times a 20 plus 1 all over 2. And at this point, this is now just arithmetic, and so you would use your calculator, and you should get 12,320. So that is how we can use those summation formulas along with the summation rules to evaluate a particular summation. Okay, and the second type of problem that we're going to look at then is use summation rules and formulas to rewrite the expression without summation notation. And what that basically means is you're going to rewrite the expression in terms of n. So we're going to use those formulas that we just looked at a little while ago to transform this expression, the summation, so that we're only looking at expressions in terms of n. And then we're going to use that new expression to find the sums when n equals 10, 100, or 1000. So in other words, it's almost as if we were doing this problem similar to the previous example, but in each of them we actually had a 10 at the top, and then a 100, and then a 1000. Now, I could do that as 3 separate problems, but that would require all of those same steps 3 times. And remember, the only thing that would change then is that at the very end, when we pull out those formulas, I would be replacing an n with either a 10, or a 100, or a 1000. So the idea is we want to try to rewrite this summation as a single formula in terms of n first, and then all we have to do is substitute the values of n into that formula at the very end of the process. All right, so first thing we're going to do here is recognize that because we're dividing by n squared, remember that I is considered the variable in this particular expression. And that means n squared in that denominator is really a constant. But remember, it's in the denominator. So what that means is this is really the same as the summation from I equals 1 up to n of I plus 4 times 1 over n squared. So we want to recognize that dividing by n squared is the same as multiplying by 1 over n squared. And now that we're multiplying by the constant, now we can move that constant out in front using our summation rule. And then now I have the summation of a sum of two terms, so now I can use the second summation rule where we can separate that. But you've got to be careful here. Remember that the 1 over n squared is multiplying with this entire summation. So when I separate this into two separate summations, remember that 1 over n squared is multiplying with the entire thing. You've got to be careful there. So this now becomes 1 over n squared times the entire sum of summation from I equals 1 to n of I plus the summation from I equals 1 up to n of 4. So now our two summations are in their simplest form where we can actually match them up to the different formulas. So this is now going to become 1 over n squared times, now remember the summation of I is going to be n times n plus 1 over 2. Plus, remember the summation of a constant is the constant times n. So this is going to just be plus 4n. Okay, now this is technically an expression without summation notation. But we do want to, for reasons that we're going to see in a couple of days, we do want to simplify this as much as possible. So the first thing I want to do is I want to actually simplify what's inside the brackets. I want to combine these two terms into a single fraction. So that means I'm going to do the following. So in the first fraction, I'm going to go ahead and distribute that n. So I now have n squared plus n over 2. Plus, now 4n, remember, in order to get this over 2, I'm going to have to multiply by a 2 over 2. So that's now going to become 8n over 2. All right, so now I've got 1 over n squared times, so now that I have a common denominator, I can add the numerators together. Notice I'm going to have an n plus an 8n, so this does become n squared plus 9n all over 2. So now we can go ahead and multiply top to top, bottom to bottom. So that's going to become n squared plus 9n over 2n squared. Now that's looking pretty simplified, but there is one more thing we can and should do, and that is to factor out an n from the numerator so that we can then simplify that with one of the n's from the denominator. And finally, we just get n plus 9 over 2n. And that is our expression without summation notation. So whatever value of n we have as our upper bound, that's what's going to replace the n's in this expression. So remember the direction said we're going to use this result to find the sums when n equals 10, when n equals 100, and when n equals 1000. Okay, so when n equals 10, that means we're going to have 10 plus 9 over 2 times 10. That's going to be 19 over 20. And that's going to be, we're just going to leave it as 19 over 20 for now. You don't need to change that to a decimal. When n is 100. Same thing. So now instead of an n, we're putting in 100 plus 9 over 2 times 100. And that's going to become 109 over 200. And finally, when n is 1000, we're going to have 1000 plus 9 over 2 times 1000. and that's going to become 1009 over 2000. If you needed to make those decimals, of course, you could just divide. All right, so these are summation rules and summation formulas. Like I said, how does this relate at all to approximating area? You're going to find that out in tomorrow's lesson. All right, good luck.